Hello and welcome to the Late Lab. Before settling in, it would be lovely to know where this video is being heard tonight. Perhaps from a quiet room at the end of the day, settling in as the world grows calmer. Maybe during a peaceful moment of rest, taking a little time to unwind, or perhaps simply listening while relaxing. Wherever this video finds you in the world, hopefully the next little while will be calm, thoughtful, and gently interesting. And while getting comfortable, please consider subscribing to the channel and leaving a like on the video if these slow journeys through science are something you enjoy. It really does help the channel continue drifting along and reach our target of 1,000 subscribers. For those who already subscribe in return for these quiet explorations of the universe, thank you. The continued support means more than can easily be said. Now, tonight's question begins with something very familiar. Light. It spills across the sky each morning, slips through windows, glints from water, and carries the colours of the world into human eyes. It moves so quickly that it feels almost instantaneous, as if the universe itself simply switches illumination on and off. But despite this effortless appearance, physics has uncovered something quietly extraordinary about light. It has a speed, not just any speed either, a very specific one. And more strangely still, that speed appears to be a limit written deeply into the structure of reality. Nothing with mass can outrun it. No signal can leap past it. No cause can travel faster than it. Light, it seems, moves at the fastest speed the universe allows. At first glance, this might seem like a simple fact of nature, perhaps no more mysterious than the boiling point of water or the colour of the sky. Yet the deeper scientists have looked, the stranger the situation has become, because the real puzzle is not that light travels quickly. The real puzzle is why the universe has a speed limit at all. Why should motion itself be capped by a particular value? Why should space and time cooperate to prevent anything from exceeding that boundary? And why does that limit appear in places far beyond light itself, shaping gravity, information, causality, and even the observable size of the cosmos? Tonight's journey will move slowly through centuries of curiosity, experiment, and imagination. From early astronomers watching distant moons flicker around Jupiter, and to physicists discovering that space and time are not quite what they appear to be. Along the way, the story of light's speed will quietly transform into something much bigger, because the more carefully physics examines this limit, the less it seems to belong to light alone. Instead, it begins to look like a rule woven into the very architecture of the universe. So let us settle in, slow things down, and explore one of the most subtle mysteries in all of science. Why light has a speed limit. Light is so familiar that it is rarely noticed. It fills rooms in the morning, glows from lamps in the evening, reflects softly from water, and paints the world in colour. Shadows stretch across pavements. Windows catch the sun and scatter it into quiet patterns across walls and floors. A warm beam of sunlight can cross a room and settle on a table without anyone thinking very much about how it arrived there. Vision itself depends on it. Every shape, every movement, every distant star that appears in the night sky reaches human awareness only because light carries that information across space. And yet, hidden inside this ordinary experience is one of the deepest discoveries ever made about the universe. Light does not move instantly. It travels. That might sound like a small detail, but it changes everything. The sunlight that reaches Earth has spent about 8 minutes crossing the distance from the sun. The glow from the moon takes just over a second to arrive. The light from the nearest stars travels for more than 4 years before it enters a telescope or touches a human eye. Even the faint glow from distant galaxies has spent millions or billions of years drifting through space before finally reaching us tonight. Every beam of light is a traveller. In daily life, this motion feels almost immediate. Light moves so quickly that it appears to fill a room all at once when a switch is flipped. Shadows snap into place in a fraction of a moment. The world seems to illuminate instantly. But physics has revealed something remarkable about that speed. Light is not only fast, it is limited, There is a specific speed at which light travels through empty space, and nothing with mass has ever been observed to exceed it. No signal can outrun it, no object can overtake it. Even gravity itself appears to respect this same limit. The universe, it seems, has a speed limit, and light happens to move exactly at that boundary. This strange rule sits quietly behind nearly everything modern physics understands about space and time. It shapes how motion works. It determines how cause and effect are allowed to unfold. It even sets the ultimate scale of what parts of the universe can ever be seen or known. Yet when people first began asking serious questions about light, none of this was obvious. For most of human history, light appeared simple and immediate. Ancient thinkers could see that light travelled in straight lines, casting sharp shadows and reflecting from polished surfaces. But the deeper nature of light remained mysterious. One of the earliest attempts to think about light systematically came from Aristotle, who considered light to be a kind of disturbance in a transparent medium. Around the same period, Ion, the mathematician hero of Alexandria, studied how light reflects from mirrors and proposed that reflected rays follow the shortest possible path between points. Even in these early ideas, the behaviour of light was beginning to look structured rather than magical. In the 9th century, the philosopher Al-Kindi examined optical phenomena in greater detail and suggested that light travels outward from luminous objects in straight rays. This idea helped shift thinking away from the older belief that vision worked because eyes emitted rays into the world. A few centuries later, the physicist and mathematician Ibn al-Haytham, working in the city of Basra and later in Cairo, carried these ideas much further. His work in optics carefully studied reflection, refraction, and vision itself. Or he demonstrated that sight occurs when light enters the eye rather than when the eye sends something outward. In doing so, he helped move the study of light away from speculation and toward careful observation and experiment. Across medieval Europe, scholars such as Robert Grosseteste continued exploring the role of light in nature. Grosseteste even proposed that light might be the fundamental agent shaping the structure of the universe, an idea that sounds strangely modern, even though it was framed in philosophical terms rather than physical equations. Taken together, these early thinkers were slowly transforming light from a poetic metaphor into a subject of natural science. Rays, reflections, colours, and lenses were no longer merely curiosities. They were clues. Still, the central question remained unsettled. What is light? Physically? For centuries, the focus of study remained closely tied to human perception. People asked how the eye works, why mirrors reflect images, and why glass bends light. These questions were practical and fascinating, but they left a deeper mystery untouched. How does light actually move through space? Does it travel instantly, arriving everywhere at once? Or does it move like sound through air or waves across water, taking time to cross distance? For a long time, the difference hardly mattered in everyday life. Light seemed so fast that it might as well have been instantaneous. But once astronomers began carefully observing the heavens, the possibility that light takes time to travel became unavoidable. When scientists finally measured that travel time, they uncovered something extraordinary. Light was not merely fast. Its speed appeared fixed, and that simple observation would eventually lead to a profound realization. The speed of light is not just a property of illumination or vision, it is woven deeply into the structure of reality itself. In the centuries that followed, the study of light would pull together ideas from optics, electricity, magnetism, relativity, quantum physics, cosmology, and even the theory of information. Each new field would approach the same strange fact from a different direction, and every one of them would arrive at the same quiet boundary. Light travels at a particular speed, and the universe does not allow anything with mass to surpass it. The deeper physicists looked, the more this limit appeared everywhere. It governs how signals move through space. It determines how clocks behave when objects travel quickly. It shapes the geometry of spacetime itself. Even the observable size of the universe depends on it. which raises a surprisingly subtle question. Perhaps the speed of a light is not really about light at all. Perhaps it is a deeper feature of reality, a rule written into the fabric of space and time long before stars began to shine. And if that is true, then the familiar glow that fills a room each morning is quietly revealing something remarkable about the universe. Light does not merely illuminate the world, it reveals the limits of how the universe itself is allowed to work. For most of human history, light appeared so fast that questioning its speed felt almost unnecessary. When a torch was lit in a dark room, the space seemed to brighten all at once. When the sun rose above the horizon, and daylight spread across the land with effortless immediacy, even reflections in mirrors appeared to happen without delay. Because of this, many ancient thinkers assumed that light travelled instantaneously, filling space the moment it was produced. This assumption was not unreasonable. In everyday life there was no obvious delay between cause and effect. If a candle was lit across the room, the flame could be seen immediately. If a lantern was raised on a distant hill, its glow appeared without hesitation. Compared to human reaction times, light simply seemed too fast to measure. Yet the question lingered quietly in the background of natural philosophy. Could light really move infinitely fast? Or did it travel across space in the same way that sound travels through air, or waves ripple across water? And early discussions rarely settled the matter. Aristotle leaned toward the idea that light behaved more like an instantaneous presence within a transparent medium. Other thinkers considered whether light might travel in rays or streams. Without precise instruments or long distances to observe, however, the difference between instantaneous motion and extremely fast motion remained almost impossible to detect. The turning point came not from studying lamps or mirrors on Earth, but from observing the skies. During the 17th century, astronomy was advancing rapidly. Telescopes were improving, star catalogues were growing more precise, and astronomers were beginning to track the movements of celestial bodies with remarkable accuracy. Among the many objects under close observation were the moons of Jupiter. One of those moons, called Io, performs a reliable and fascinating dance. Io circles Jupiter roughly once every 42 hours. As it moves around the giant planet, it periodically passes into Jupiter's shadow and disappears from view before reappearing again. These eclipses occur with striking regularity, making them valuable cosmic clocks. Astronomers realized that by carefully recording the timing of these eclipses, they could predict when Io would vanish and reappear during each orbit. Over time, a detailed schedule of these events began to emerge. In the late 17th century, the Danish astronomer Ole Rømer was studying these observations while working at the Paris Observatory. Rømer had been invited to Paris by Giovanni Domenico Cassini, one of the leading astronomers of the era. Cassini and his colleagues were deeply involved in tracking the motions of planets and moons, compiling tables that would allow astronomers across Europe to predict celestial events with increasing precision. While examining the recorded eclipses of Io, Rømer noticed something strange. The timing of Io's eclipses did not remain perfectly consistent. Sometimes the moon seemed to disappear slightly earlier than expected. At other times, it vanished a little later than predicted. At first glance, such discrepancies might have suggested errors in observation or calculation, but the pattern was too systematic to ignore. When Earth was moving toward Jupiter in its orbit around the Sun, Io's eclipses appeared to happen slightly earlier than expected. When Earth was moving away from Jupiter, the eclipses appeared slightly delayed. Rømer began to suspect that the explanation might lie not in Io's motion, but in the travel time of light itself. If light required time to cross the vast distance between Jupiter and Earth, then the changing distance between the two planets would slightly alter when the eclipses appeared to occur. When Earth moved closer to Jupiter, light would have a shorter journey to travel. When Earth moved farther away, light would take longer to arrive. In 1776, Rømer presented this explanation to the French Academy of Sciences. His conclusion was simple but profound. The delays in Io's eclipses suggested that light does not arrive instantly. Instead, it moves across space at a finite speed. By examining how much the timing shifted as Earth's distance from Jupiter changed, Römer estimated that light required several minutes to cross the diameter of the Earth's orbit around the Sun. His calculation was not perfectly accurate by modern standards, but it was remarkably close considering the tools available at the time. For the first time, there was strong empirical evidence that light travels. The discovery did not emerge in isolation. It was the result of a growing culture of careful astronomical observation. Cassini and his colleagues had spent years refining measurements of planetary motion. Telescopes had become more capable, and astronomers were learning to track celestial patterns with increasing patience and precision. Equally important were improvements in timekeeping. Accurate clocks allowed observers to record events with far greater reliability than before. The measurement of light speed depended not only on observing distant moons, but also on measuring time with confidence. In this sense, the discovery that light has a finite speed was not a single flash of insight. It was the product of many developments unfolding together across astronomy, instrumentation, and mathematics. The idea soon attracted the attention of other thinkers. Among them was the Dutch scientist Christian Huygens, who took Römer's observations and attempted to calculate the speed of light more carefully. Huygens estimated that light travels at an enormous velocity, far greater than anything familiar in everyday life. Huygens was already developing another influential idea about light. Rather than imagining light as tiny particles flying through space, he proposed that light behaves as a wave spreading through a medium. This idea became known as the wave theory of light. Although the details of that theory would evolve over time, Huygens' work helped shift thinking about light into a more mechanical and physical framework. Light was no longer simply a mysterious illumination that appeared instantly. It became something that moves, propagates, and obeys laws that can be studied. Other thinkers of the era were also trying to understand nature through mechanical principles. The Dutch philosopher Isaac Beeckman had explored the idea that physical processes might be explained through motion and geometry rather than mystical qualities. René Descartes developed sweeping mechanical descriptions of the universe in which matter and motion governed everything from planetary orbits to optical effects. Not all of these ideas proved correct. Some were later replaced by more accurate theories, but together they reflected a profound shift in how scientists approached the natural world. Nature was no longer viewed as a collection of mysterious phenomena waiting to be interpreted symbolically. Instead, it was increasingly treated as a system governed by measurable processes unfolding through space and time. Once light was shown to require time to travel, its philosophical role changed immediately. If light takes time to cross distance, then every act of seeing becomes a small journey through the past. When someone looks at the moon, the image arriving in the eye shows the moon as it was a little more than a second ago. When a telescope observes a distant star, the light entering the instrument may have begun its journey years earlier. In other words, vision is never truly immediate. Light carries information through space, and that information arrives after a delay determined by the distance it must travel. This realization quietly reshaped humanity's understanding of the universe. The night sky was no longer a collection of objects seen in the present moment. It became a record of events unfolding across time. Light had revealed something remarkable. The universe does not merely exist in space. It unfolds through time, carried to us by travelling beams of illumination that move at a finite speed across the vast distances between worlds. Once astronomers realized that light required time to travel across space, the next challenge naturally followed. If light had a speed, then perhaps that speed could be measured more directly. The observations of Jupiter's moon, Io, had revealed an important truth, but they relied on vast cosmic distances and complex orbital predictions. Astronomical evidence could show that light was not instantaneous, yet it still left room for uncertainty about the exact value of its speed. During the 18th and 19th centuries, science began to shift towards something new. Rather than relying solely on distant celestial events, researchers increasingly sought to recreate natural phenomena inside controlled experiments. The laboratory became a place where nature could be examined carefully, repeatedly, and with improving precision. Light soon became a perfect subject for this new style of investigation. The problem was not trivial. Light travels extraordinarily fast, crossing distances that would take sound hours or days in the blink of an eye. Any attempt to measure such motion directly required ingenious methods and delicate instruments. One of the first successful terrestrial experiments was performed by the French physicist Hippolyte Fizeau in the 1840s. Fizeau designed a clever apparatus that used a rapidly rotating toothed wheel, a distant mirror, and a carefully aligned beam of light. The idea was deceptively simple. A beam of light was sent through the gaps between the teeth of the spinning wheel and travelled across open air to a mirror several kilometres away. The mirror reflected the beam back toward the wheel. If the wheel rotated slowly, the returning beam could pass back through the same gap and reach the observer's eye. But as the wheel spun faster, something curious began to happen. At certain speeds, the returning light was blocked by the next tooth of the wheel instead of passing through the gap. The wheel had turned just enough during the light's round trip to intercept the beam. By carefully measuring the rotation speed of the wheel and the distance travelled by the light, Fizeau could estimate how long the light had taken to complete its journey. From that travel time, he calculated the speed of light. The result was astonishingly close to modern measurements. Fizeau's experiment showed that light travels at roughly 300,000 kilometers per second. Even with the modest instruments of the mid-19th century, the result demonstrated that light speed could be determined within surprisingly narrow limits. Shortly afterward, another French physicist, Léon Foucault, refined the method using a rotating mirror instead of a toothed wheel. In Foucault's arrangement, a beam of light reflected from a spinning mirror and travelled toward a distant stationary mirror before returning. Because the mirror had rotated slightly during the light's journey, the returning beam appeared displaced by a tiny angle. By measuring that displacement and the mirror's rotation rate, Foucault obtained an even more precise estimate of light speed. His method also allowed scientists to compare how light travelled through different materials such as air and water, helping clarify competing theories about the nature of light itself. And these experiments marked a quiet but important transformation in science. The speed of light was no longer inferred from distant moons and planetary motions alone. It had become something that could be measured inside carefully designed instruments on Earth. Across Europe and North America, laboratories began refining these techniques further. Among the most influential experimenters was the American physicist Albert A. Michelson. Michelson devoted much of his career to measuring the speed of light with extraordinary accuracy. Using improved versions of the rotating mirror method, along with longer experimental paths and more stable optical systems, Michelson repeatedly refined the measurement throughout the late 19th century. His dedication to precision was remarkable. Michelson understood that even small improvements in measurement could reveal whether the speed of light remained perfectly constant or showed subtle variations under different conditions. Over time, his results became some of the most accurate physical measurements ever made. Michelson's work also reflected a broader movement in 19th century science known as metrology, the study of measurement itself. Scientists were increasingly concerned with defining fundamental constants of nature and determining their values as precisely as possible. These constants included quantities such as the charge of the electron, the gravitational constant, and the speed of light. Each represented a kind of numerical fingerprint of the universe, a value that appeared to remain stable across all experiments and observations. Armand Fizeau, the brother of Hippolyte Fizeau, played an important role in advancing experimental optics during this period as well. Through careful optical experiments and improvements to instrumentation, researchers like the Fizeau family contributed to a growing culture of exact measurement that would define modern physics. Why did such precision matter so much? At first glance, the difference between two measurements of light speed might appear trivial. Whether light travelled slightly faster or slightly slower seemed unlikely to change everyday life, but for physicists the implications were profound. The more accurately light speed was measured, the more consistently it appeared to hold the same value. It did not fluctuate randomly with location, season, or the motion of the observer. Instead, it behaved as though the universe itself had chosen a specific number and refused to deviate from it. This stability hinted that the speed of light might not simply be a property of a particular substance or phenomenon. It might be something more fundamental, woven into the structure of nature itself. As experimental techniques improved, the measured value became increasingly precise. Light appeared to travel at approximately 299,792 kilometers per second through empty space. Even small experimental uncertainties began shrinking as instruments improved. Eventually, the relationship between light and measurement became even deeper. In the 20th century, scientists began redefining units of measurement in terms of universal physical constants, rather than physical objects. For centuries, the meter had been defined using metal bars stored in carefully controlled conditions, but these physical standards could expand, contract, or suffer tiny imperfections. Light offered something better. Because its speed appeared constant everywhere in the universe, it could serve as a stable reference for defining distance itself. Today, the meter is defined in terms of how far light travels in a precise fraction of a second. In other words, humanity's measurement of space is now tied directly to the behaviour of light. This shift reveals just how deeply light has become embedded in our understanding of the physical world. What began as an attempt to measure a beam crossing a field has grown into a system in which the very definition of distance depends on light's motion. And yet, the deeper scientists looked, the stranger the situation became. With each improvement in precision, the speed of light appeared more stable and universal. It did not seem to depend on the motion of its source, or the direction in which it travelled. No experiment revealed an easy way to make it go faster or slower. Instead of behaving like an ordinary speed that could vary under different conditions, it began to look more like a built-in feature of the universe, a constant. And that realization would soon lead physicists toward one of the most revolutionary ideas ever proposed about space, time, and motion. By the middle of the 19th century, the speed of light had begun to look less like a curious measurement and more like a clue. The number itself appeared stable, reproducible, and strangely universal. But scientists still did not fully understand what light actually was. Was it a stream of tiny particles, a vibration in some invisible medium, or something else entirely? At the same time, another mystery was unfolding in physics, one that at first seemed unrelated to light: electricity and magnetism. For centuries, these two phenomena had fascinated observers. Amber rubbed with cloth could attract small objects. Lodestones could pull iron filings toward them with invisible force. Lightning split the sky during storms, while simple electrical machines could produce sparks indoors. These effects seemed dramatic but disconnected, like scattered pieces of a puzzle whose picture was not yet clear. Gradually, scientists began to notice that electricity and magnetism were not separate curiosities at all. They were deeply connected. The French physicist André-Marie Ampère demonstrated that electric currents produce magnetic effects. Wires carrying electricity could push and pull on each other in predictable ways, behaving almost like tiny magnets. Around the same time, the mathematician Carl Friedrich Gauss developed powerful mathematical tools for describing how forces spread through space, providing a way to analyze invisible influences such as gravity, electricity, and magnetism. These discoveries hinted that the world might contain hidden structures, linking electrical and magnetic behaviour together. But it was the work of Michael Faraday that introduced one of the most important conceptual shifts in the entire history of physics. Faraday had little formal mathematical training, yet his physical intuition was extraordinary. Through careful experiments in the early 1800s, he demonstrated that changing magnetic fields could generate electric currents. This phenomenon became known as electromagnetic induction, and eventually formed the foundation of modern electric generators. More importantly, Faraday introduced a new way of thinking about forces. Before Faraday, many scientists imagined forces as acting directly between objects across empty space. Two charged bodies attracted or repelled each other. But the mechanism behind that interaction remained mysterious. It was often described simply as action at a distance. Faraday proposed something different. Instead of imagining forces jumping directly between objects, he suggested that space itself might contain structures capable of carrying influence. Then he visualized lines of force spreading outward from magnets and electric charges, forming patterns throughout the surrounding region. These lines were not merely diagrams drawn on paper. Faraday believed they represented real physical conditions in space. In this view, the presence of an electric charge altered the surrounding environment, creating an electric field. A magnet created a magnetic field. When other objects entered those regions, they responded to the structure already present in the space around them. The idea was revolutionary. Forces were no longer mysterious connections between distant objects. They were properties of fields filling space itself. This concept would soon transform the study of light. The person who translated Faraday's intuitive ideas into precise mathematical form was the Scottish physicist James Clerk Maxwell. Maxwell was one of the rare scientists capable of combining deep physical insight with extraordinary mathematical skill. During the 1860s, he began developing a comprehensive theory describing how electric and magnetic fields behave and interact. The result became known as Maxwell's equations. These equations describe how electric fields and magnetic fields change in response to charges, currents, and each other. One of Maxwell's most remarkable discoveries was that changing electric fields create magnetic fields, and changing magnetic fields create electric fields. This mutual relationship suggested something extraordinary. If a changing electric field produces a magnetic field, and that magnetic field in turn produces another electric field, then the process could continue indefinitely. The disturbance would sustain itself, propagating through space as a wave. Maxwell realized that his equations predicted the existence of electromagnetic waves. Even more surprising was the speed at which these waves should travel. When Maxwell calculated the propagation speed implied by his equations, he obtained a value that closely matched the measured speed of light. The agreement was far too precise to be a coincidence. Maxwell reached a stunning conclusion. Light itself must be an electromagnetic wave. What people had been calling light for centuries was simply a visible portion of a much broader phenomenon. Oscillating electric and magnetic fields were spreading through space, and human eyes happened to detect only a narrow range of their frequencies. In one elegant insight, Maxwell unified optics with electricity and magnetism. The glow of a candle, the spark of static electricity, and the invisible forces surrounding a magnet were all expressions of the same underlying physics. This realization expanded the idea of light dramatically. If visible light was only one example of electromagnetic waves, then many other kinds of waves might exist as well, beyond the range of human vision. That prediction was confirmed a few decades later by the German physicist Heinrich Hertz. In the late 1880s, Hertz built apparatus capable of generating and detecting electromagnetic waves in the laboratory. Using metal conductors and spark gaps, he produced oscillating electrical currents that created waves travelling through space. These waves behaved exactly as Maxwell's theory predicted. They reflected from surfaces, interfered with each other, and propagated at the speed expected from the equations. Hertz had demonstrated the existence of electromagnetic radiation beyond visible light. Today these waves are known as radio waves, and they form the foundation of modern communication technologies. But in Hertz's time, their importance was primarily scientific. They confirmed that Maxwell's theory described a real and fundamental property of nature. Visible light was only one small part of a vast electromagnetic spectrum. Radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays, and gamma rays all belong to the same family. They differ only in their wavelengths and frequencies, yet they all travel through empty space in the same way. And all of them move at the same speed. This insight deepened the mystery surrounding the speed of light. If many different forms of electromagnetic radiation share the same velocity, then that speed cannot be a special property of visible light alone. It must arise from something more fundamental. Another important contributor helped clarify Maxwell's theory further. The English physicist Oliver Heaviside reformulated Maxwell's equations into a more compact and elegant mathematical structure. His work simplified the original expressions and produced the modern vector form widely used in physics today. Heaviside's contribution illustrates an important feature of scientific progress. Major discoveries often become clearer as later researchers refine and reorganize earlier work. Maxwell's original theory contained the essential insight, but Heaviside's mathematical treatment made the theory easier to understand and apply. Together, these developments transformed the study of light completely. Light was no longer simply a beam travelling through space. It was an oscillation of electric and magnetic fields, a dynamic ripple spreading through the structure of the electromagnetic field itself, and the speed of that ripple appeared to be determined by the properties of empty space. In Maxwell's theory, the speed of electromagnetic waves depends on two fundamental quantities, describing how electric and magnetic fields behave in a vacuum. When those quantities are combined mathematically, either the resulting speed matches the measured velocity of light. This meant that light speed was not imposed externally by some mechanical constraint. It emerged naturally from the physical properties of space. The vacuum was no longer an empty void. It possessed measurable characteristics governing how electromagnetic fields propagate. Light travelled at its particular speed because that speed was built into the structure of the electromagnetic field. For the first time, physicists could see that the speed of light might reflect something deeper about the universe itself. It was not merely a number describing how quickly a beam crossed a room or travelled from the sun to Earth. It was a fundamental feature of nature's architecture, and that realization would soon lead scientists toward an even more astonishing idea. The speed of light might not simply describe how electromagnetic waves move, it might define how space and time themselves are allowed to behave. By the late 19th century, physicists had arrived at a remarkable conclusion. Light was not a stream of particles shooting through empty space. According to the theory developed by James Clerk Maxwell, light was an electromagnetic wave, a ripple formed by oscillating electric and magnetic fields spreading outward through space. But this realization introduced a new puzzle almost immediately. Every wave that people understood at the time required a medium. Sound waves travel through air because air molecules push and pull against each other. Water waves travel across the surface of the sea because water itself rises and falls in motion. Even vibrations in a violin string require the physical substance of the string to carry the disturbance. So if light was a wave, then what exactly was waving? This question seemed unavoidable. Waves needed something to move through, something capable of supporting oscillations. If light travelled through empty space between stars, then space itself must contain some kind of invisible substance capable of carrying electromagnetic vibrations. Physicists gave this hypothetical medium a name, the luminiferous ether. The word ether had a long history in philosophy, but 19th century scientists treated it as a physical hypothesis rather than a mystical concept. The ether was imagined as an extremely subtle substance filling all of space. It would need to be incredibly transparent so that light could travel through it without resistance, and yet also elastic enough to support rapid oscillations. In some ways, it was a strange material. The ether would have to fill the entire universe, penetrate all matter, and remain undetectable by ordinary means. Yet these peculiar features did not seem unreasonable at the time. After all, light had to be moving through something. This assumption was so natural that very few physicists initially questioned it. Instead, the challenge became understanding the properties of the ether and how objects move through it. Several scientists proposed different models. The British physicist George Gabriel Stokes suggested that the ether might behave somewhat like a fluid that flows around objects moving through it. In his picture, the Earth might drag some of the ether along as it travelled through space, making the motion difficult to detect. Others took a different approach. The Dutch physicist Hendrik Lorentz developed a detailed theoretical framework in which the ether remained completely stationary, while matter moved through it. Lorentz's work focused on how electric charges and electromagnetic fields behaved inside this invisible medium. At the same time, the Irish physicist George Fitzgerald was considering how motion through the ether might affect physical objects themselves. Together, these researchers were attempting to reconcile Maxwell's electromagnetic theory with the idea that the Earth was moving through an all-pervading ether. If the ether truly filled space, then the Earth should be travelling through it as our planet orbited the Sun. That motion should create an effect similar to wind moving through the atmosphere. Just as a moving bicycle rider feels air rushing past, the Earth might experience a kind of ether wind as it moved through this invisible medium. If such a wind existed, then light travelling in different directions relative to that motion should appear to move at slightly different speeds. Detecting that difference became one of the most important experimental goals of the era. Among the scientists who pursued this challenge was Albert A. Michelson, whose earlier experiments had already produced extremely precise measurements of light's speed. Michelson believed that careful optical experiments might detect the subtle effects of Earth's motion through the ether. Working with the chemist Edward Morley, Michelson constructed a delicate instrument known as an interferometer. This device split a beam of light into two perpendicular paths, allowing the beams to travel different directions before recombining. If the Earth were moving through the ether, then light travelling along one direction should take slightly longer than light travelling along the other. When the beams recombined, that difference in travel time would create a detectable shift in the interference pattern of light. The experiment required extraordinary precision. The expected difference in travel time was extremely small, roughly comparable to measuring variations in motion of a few parts in hundreds of millions. Michelson and Morley performed the experiment in 1887. The result was surprising. No difference appeared. The interference pattern remained unchanged regardless of the orientation of the apparatus or the motion of the Earth around the Sun. According to the experiment, our light travelled at the same speed in all directions. At first glance, this result seemed deeply puzzling. If the ether existed and the Earth was moving through it, then the ether wind should have affected the light beams in the experiment. Yet nothing of the sort appeared. The Michelson-Morley experiment is often presented as a dramatic turning point that instantly destroyed the ether theory. In reality, the situation was more complicated. Many physicists did not immediately abandon the ether. Instead, they began developing increasingly creative explanations for why the expected ether wind could not be detected. One of these explanations came from George Fitzgerald. He suggested that objects moving through the ether might physically contract in the direction of motion. If the experimental apparatus itself shrank slightly along its direction of travel, then the expected time difference between the two light paths might cancel out. Hendrik Lorentz developed this idea further. In his electron theory of matter, Lorentz proposed that motion through the ether caused real physical changes in the structure of objects and in the behaviour of electromagnetic forces. These adjustments could conceal the effects of motion through the ether, making it appear as though the ether wind did not exist. This concept became known as the Lorentz-Fitzgerald contraction. In this interpretation, the ether remained real, but its effects were hidden by subtle changes in the lengths of objects and the timing of physical processes. Over time, additional experiments continued probing the problem. The Kennedy-Thorndike experiment, conducted in the early 20th century, tested whether changes in Earth's speed through space might influence measurements of light's velocity over time. Like the Michelson-Morley experiment, the results showed no detectable variation. Gradually, a pattern began to emerge. Different experiments, conducted with different methods and increasing precision, all seem to point in the same direction. No matter how carefully scientists searched, they could not detect any motion through the ether. The expected ether wind remained stubbornly absent. This growing body of evidence placed physicists in an uncomfortable position. The ether seemed necessary to explain how electromagnetic waves propagated, yet every attempt to observe its effect failed. Common sense suggested that waves required a medium, but nature refused to cooperate. The situation created a quiet tension within physics. On one hand, Maxwell's equations describing electromagnetic waves were enormously successful. On the other hand, the medium those waves were supposed to travel through remained completely invisible and undetectable. The ether was becoming increasingly strange. It had to fill all space. It had to allow planets and stars to pass through it freely. It had to transmit electromagnetic waves at enormous speeds, and yet it left no measurable trace of its existence. Physicists were slowly being pushed toward an unsettling possibility. Perhaps the assumption that waves must always travel through a material medium was wrong. If that idea were abandoned, then light might not require an ether at all. But rejecting the ether would mean rethinking some of the most basic assumptions about space, as motion and time themselves. The stage was quietly being set for one of the most profound transformations in the history of science. Common sense insisted that waves needed something to move through, yet the universe seemed determined to show otherwise. As the 19th century came to an end, physics found itself in an increasingly strange situation. The theory of electromagnetism developed by James Clerk Maxwell worked beautifully. It explained electricity, magnetism, and light with remarkable accuracy. Yet the deeper implications of that theory seemed to collide with long-held assumptions about motion and time. The speed of light appeared to remain constant no matter how carefully it was measured. This behaviour seemed almost impossible under the traditional framework of physics inherited from Isaac Newton. In the Newtonian picture of the universe, time flowed the same way for everyone everywhere. Space formed a fixed stage on which objects moved. Motion could always be described relative to this background of absolute space and absolute time. Within that framework, speed should add together in a simple and intuitive way. If a train moves along a track and someone throws a ball forward inside the carriage, the speed of the ball relative to the ground becomes the speed of the train plus the speed of the throw. This rule works well for everyday motion and had been accepted for centuries. But light refused to behave this way. Repeated experiments suggested that light's speed did not increase when its source was moving. No matter how the observer or the source of light moved, the measured speed remained the same. This strange result stood quietly in the background of late 19th century physics like an unsolved riddle. Several thinkers were already circling around the implications. One of the most important was the French mathematician and physicist Henri Poincaré. Poincaré was deeply interested in the foundations of physics and the symmetry of natural laws. He argued that the laws of nature should appear the same for observers moving at constant speed relative to one another, an idea known as the principle of relativity. This principle had already existed in a limited form within Newtonian mechanics. Galileo Galilei had earlier observed that experiments conducted inside a smoothly moving ship would behave the same as those performed on land. From inside the cabin, it was impossible to tell whether the ship was moving or stationary. Poincaré extended this reasoning to electromagnetism. If Maxwell's equations described real laws of nature, then they too should obey the principle of relativity. Observers moving at constant velocity should still see the same electromagnetic behaviour, but Maxwell's equations contained something unusual. They predicted a specific speed for electromagnetic waves, which matched the measured speed of light. This raised a difficult question. Relative to what was that speed defined? For many physicists, the answer had been the ether. The ether would provide a universal reference frame against which the motion of light could be measured. Yet experiments searching for motion through the ether had repeatedly failed. Poincaré recognized that the problem ran deeper than a missing substance. He explored how observers might synchronize clocks using light signals, and considered how the measurement of time itself depended on conventions adopted by observers. At the same time, Hendrik Lorentz had already developed the mathematical tools needed to reconcile Maxwell's equations with the principle of relativity. Lorentz introduced transformations that described how space and time coordinates must change when moving between observers travelling at different velocities. These relationships became known as the Lorentz transformations. In Lorentz's own interpretation, these mathematical adjustments were physical effects caused by motion through the ether. Objects moving through the ether might contract slightly, and clocks might tick at slightly different rates. These distortions could hide the motion relative to the ether, preserving the appearance that light travelled at the same speed for all observers. The mathematics worked. But the explanation remained complicated. Then, in the year 1905, a young physicist working at the Swiss Patent Office proposed a remarkably simple shift in perspective. His name was Albert Einstein. Einstein approached the puzzle from a different angle. Rather than attempting to explain why the speed of light seemed constant despite motion, he suggested that the constancy of light's speed should be treated as a fundamental principle of nature. Instead of asking how the laws of physics might adjust to hide motion through the ether, Einstein asked a more radical question. What if there was no ether at all? Einstein's special theory of relativity began with two simple postulates. The first stated that the laws of physics are the same for all observers moving at constant velocity relative to one another. No experiment performed in such a frame can reveal whether that frame is moving or stationary. The second postulate declared that light in a vacuum always travels at the same speed, regardless of the motion of the observer or the source. Taken together, these two ideas forced a profound change in how motion must be understood. If every observer measures the same speed for light, then space and time cannot remain fixed and absolute in the way Newton had imagined. Instead, measurements of distance and duration must depend on the relative motion of the observer. Time itself becomes flexible. Clocks moving relative to one another tick at different rates. There are objects moving at high speeds shortened slightly in the direction of the motion. Events that appear simultaneous for one observer may occur at different times for another. These effects are not merely illusions or measurement errors. They are genuine features of the structure of space-time. The Lorentz transformations that Hendrik Lorentz had introduced earlier suddenly took on a new meaning. Rather than describing distortions caused by motion through an ether, they revealed the natural geometry of space and time when the speed of light is treated as an invariant limit. Einstein did not invent the mathematical machinery from scratch. Much of it already existed through the work of Lorentz, and through insights developed by Henri Poincaré. What Einstein provided was a new conceptual interpretation. He removed the ether entirely and treated the constancy of light speed as a fundamental property of reality. Once that step was taken, the strange experimental results that had puzzled physicists for decades suddenly became natural consequences of the theory. The speed of light was no longer merely the speed of a particular phenomenon. It became a universal limit built into the structure of space-time itself. In this new picture, the speed of light defines the boundary between what can influence what. No information, signal, or physical object carrying mass can exceed this speed. Cause and effect themselves are constrained by this limit. Two observers moving relative to one another may disagree about distances and durations, but they will always agree about the speed of light. The implications of this idea extend far beyond optics, and special relativity reshaped the understanding of motion, energy, and matter. It eventually led to the famous relationship between mass and energy, expressed through the statement that energy equals mass, multiplied by the square of the speed of light. Even more importantly, it revealed that the speed of light is not simply about light. It is about the architecture of the universe. The constancy of that speed tells every observer how space and time must behave. It governs how quickly signals can propagate, and how different observers connect their measurements of events. What began as a puzzle about beams of light moving through space had quietly transformed into a deeper discovery. The speed of light is woven into the very structure of reality itself. The ideas introduced by Albert Einstein in the early 20th century changed the rules of motion, but at first they still appeared somewhat abstract. Space and time seemed to stretch and compress depending on how an observer moved. Clocks could tick at different rates. Lengths could shrink when objects travelled very quickly. These effects were precise and testable, yet they also felt unusual because they were described mostly through algebra and transformation rules. A deeper understanding began to emerge when the mathematician Hermann Minkowski reinterpreted Einstein's theory in geometric terms. Minkowski had once been one of Einstein's teachers, and he recognized that the strange relationships appearing in special relativity were not merely curious adjustments to classical physics. Instead, they revealed a new structure for the universe itself. In 1908, Minkowski presented a striking idea. Space and time, he suggested, should no longer be treated as separate ingredients of reality. They form a single four-dimensional structure. He called this structure spacetime. In everyday experience, space feels like the three directions through which objects can move, while time feels like a separate flow that carries events forward. Minkowski's insight was that these distinctions depend on the observer. Different observers moving relative to one another slice space-time in different ways when they measure distances and durations. In other words, space and time are not independent backgrounds. They are woven together. This new geometric perspective allowed physicists to visualize the structure of relativity more clearly. Instead of thinking only in terms of moving objects and ticking clocks, one could imagine events plotted within a four-dimensional landscape. Each event in the universe occupies a specific location in space and a specific moment in time. Together, these coordinates define a point in space-time. When physicists draw simplified diagrams of this structure, they usually represent time as a vertical direction and space as horizontal directions. These diagrams are not complete pictures of the universe, but they reveal something essential about how cause and effect operate. Within these diagrams, light plays a special role. Imagine a flash of light emitted from a particular event in space-time. The light spreads outward in all directions, forming an expanding sphere as it travels through space. If this expansion is drawn on a space-time diagram, the surface traced out by the advancing light forms a shape known as a light cone. The light cone represents all possible paths that light can take as it moves away from that event. Anything inside the cone corresponds to events that could be influenced by the original event through signals travelling at or below the speed of light. Anything outside the cone lies beyond the reach of influence from that event. This structure divides space-time into distinct regions. Events that lie within the light cone are said to have a time-like relationship with the original event. This means that one event could potentially influence the other through signals or physical interactions moving slower than light. Events that lie exactly on the surface of the cone are described as light-like. These events can be connected only by signals travelling at the speed of light itself. Events that lie outside the cone are called space-like separated. No signal travelling at or below the speed of light can connect them. This geometric distinction expresses something profound about causality. The structure of space-time determines which events can influence which others. The speed of light appears here not simply as a fast velocity, but as a boundary that shapes the possible connections within the universe. If the space-time diagram is imagined visually, the paths of objects moving through time appear as lines within this geometry. These paths are called world lines. An object moving slowly traces a world line that stays well inside the light cone. As the object moves faster, the slope of its path approaches the boundary of the cone. But no object carrying mass can ever tilt its world line enough to reach or cross the light-like surface itself. Light alone travels exactly along that boundary. Seen from this perspective, the speed of light is not merely a property of electromagnetic radiation. It is the slope that defines the edge of causal influence within space-time. Every observer, no matter how they move, agrees on this boundary. That agreement is one of the deepest symmetries in nature. This geometric viewpoint also explains why objects with mass cannot reach the speed of light. As an object accelerates and approaches that boundary, the structure of space-time forces the energy required for further acceleration to grow dramatically. Reaching the boundary would require unlimited energy, which nature never provides. Light does not face this restriction because it has no rest mass. Its world line naturally follows the light-like direction embedded in the geometry of space-time. Minkowski's formulation made relativity far easier to understand conceptually. What had once seemed like a collection of strange rules about clocks and rulers now appeared as consequences of a deeper geometric framework. Distances and durations are not absolute because they depend on how different observers move through space-time. Yet the underlying geometry remains consistent for everyone. In this sense, space-time itself becomes a physical structure. The mathematician Hermann Weyl later extended these ideas while exploring the geometric interpretation of fields. Weyl emphasized that the mathematical descriptions used in relativity were not merely abstract tools. They corresponded to real features of the physical world. Geometry in this context was not just a language for describing motion, it determined what kinds of motion were possible. This shift in perspective marked a quiet but profound transformation in physics. Instead of imagining forces acting across empty space, physicists increasingly describe the universe as a structured geometry in which objects and fields evolve. Within that geometry, the speed of light defines a fundamental boundary. Signals cannot outrun it. Influence cannot leap across space-time faster than it allows. Even gravity, as later described in general relativity, respects the same limit when changes in gravitational fields propagate through the universe. Light therefore serves as a kind of messenger that reveals the structure of space-time itself. It traces the edges of the cones that divide possible futures from unreachable elsewhere. It outlines the limits within which events can affect one another. When viewed this way, the original question about why light has a speed limit begins to look slightly different. The limit does not arise because light happens to move slowly enough to be restricted. Instead, light moves exactly along the boundary already built into the geometry of space-time. It follows the paths that the universe itself makes available. The familiar beam of light crossing a room, or the distant glow of a star arriving after years of travel, is quietly tracing the architecture of reality. Light is not simply a traveller within the universe. It reveals the shape of the stage on which everything else unfolds. Time appears simple in everyday life. Clocks tick steadily. Moments pass in a quiet and orderly sequence. People agree when events occur. A train departs at a certain hour. A bell rings at a certain minute. A sunrise marks the beginning of a new day. It is easy to assume that time flows the same way everywhere, like a universal river carrying every observer along together. Yet the theory of relativity reveals that time is far more subtle than that. Once the speed of light is treated as a universal constant, the measurement of time itself becomes deeply connected to how light signals move between observers. In modern physics, time is not defined by some invisible cosmic clock ticking in the background. Instead, time is defined operationally by how observers exchange signals and compare clocks. Imagine two clocks placed some distance apart. To say that these clocks show the same time, an observer must find some method of synchronizing them. In practice, the most reliable way to do this involves sending light signals back and forth. One clock sends a flash of light to the other. The second clock reflects the signal back. By measuring the travel time of the light, and assuming that light travels at the same speed in both directions, the observers can adjust their clocks so that they remain synchronized. This procedure sounds almost trivial, yet it hides an important idea. The very definition of simultaneous time readings depends on the behaviour of light. Albert Einstein recognized this connection while developing special relativity. If the speed of light is always the same for all observers, then the process of synchronizing clocks becomes dependent on the observer's motion. Two observers moving relative to one another may disagree about whether distant clocks are synchronized. This leads to one of the most surprising consequences of relativity. Simultaneity itself becomes relative. To see how this works, imagine a long train moving smoothly along a straight track. Suppose two lightning strikes occur at opposite ends of the train. An observer standing on the platform exactly midway between the two strikes sees the flashes arrive at the same moment and concludes that the strikes occurred simultaneously. But an observer sitting at the centre of the moving train sees something different. Because the train is moving forward, the observer inside the train moves toward the flash coming from the front and away from the flash coming from the rear. As a result, the front flash reaches the observer slightly earlier than the rear flash. From the train observer's perspective, the lightning strike at the front must have occurred before the strike at the rear. Otherwise, the flashes would not have arrived in that order. Both observers use the same speed of light. Both make careful measurements. Yet they disagree about the timing of the events. This is not a mistaken observation. It is a real feature of space-time. Events that appear simultaneous for one observer may occur at different times for another observer moving at a different velocity. The order of events remains consistent whenever cause and effect are involved, but the timing of distant events can vary depending on the observer's motion. Closely related to this idea is time dilation. If two observers move relative to one another, each observer measures the other's clock as ticking more slowly than their own. This effect becomes noticeable only at extremely high speeds, but it has been confirmed repeatedly in experiments. One of the earliest experimental tests was carried out by Herbert Ives and G.R. Stilwell in the 1930s. Their work examined the frequency of light emitted by fast-moving atoms and confirmed the relativistic predictions for how motion affects time and frequency. Later experiments used unstable particles known as muons, which are produced when cosmic rays strike the upper atmosphere. Muons normally decay in a tiny fraction of a second, yet when they move at speeds close to the speed of light, their internal clocks appear to run more slowly from the perspective of observers on Earth. Because of this time dilation, many muons survive long enough to reach the surface of the planet. Without the relativistic slowing of their internal processes, they would decay long before completing the journey. More recent experiments rely on extraordinarily precise atomic clocks. These clocks measure time by tracking the vibrations of atoms, which oscillate with remarkable regularity. Institutions such as the National Institute of Standards and Technology in the United States, along with international timing laboratories around the world, maintain networks of atomic clocks capable of measuring time with extraordinary precision. When identical clocks are placed on aircraft and flown around the Earth, their readings differ slightly from clocks left on the ground. These differences arise from the combined effects of motion and gravity predicted by relativity. Even satellites in the global positioning system must account for time dilation in order to function accurately. Without relativistic corrections, navigation errors would accumulate rapidly. These experimental confirmations make it clear that the effects described by relativity are not abstract thought experiments. They occur constantly in the real world. Early in the development of relativity, many mathematicians and philosophers explored the implications of these ideas. Figures such as Emile Borel contributed to discussions about the logical structure of time and simultaneity. Meanwhile, Vladimir Varychak examined how the geometry of space-time might be understood through alternative mathematical representations. These debates reflected how deeply relativity challenged earlier assumptions. For centuries, ESA's time had been treated as a universal background against which events unfolded. Relativity replaced that image with a far more flexible structure. Time becomes something that observers measure through physical processes rather than something that exists independently of those processes. Light plays a central role in this framework because it provides the signals used to compare clocks and define simultaneity. The speed of light therefore enters directly into the operational definition of time itself. Two observers who exchange light signals can establish how their clocks relate to one another. Yet because the speed of light remains constant for both observers, their measurements of time and distance must adjust accordingly. The result is a universe in which temporal order is shaped by the same boundary that limits the motion of signals. In this sense, the speed of light is not simply the fastest possible speed for objects moving through space. It is also the principle that determines how time itself is organized. Events can influence one another only if signals traveling at or below that speed can connect them. Simultaneity becomes relative because different observers draw different slices through space-time when they measure time. The quiet tick of a clock is therefore not as universal as it once seemed. Behind every measurement of time lies an exchange of light signals moving through space-time. The structure of those signals defines which events can be considered simultaneous and which must unfold in sequence. The universe keeps time, but it does so according to rules shaped by the same speed that governs the motion of light itself. The strange behaviour of time in relativity is often discussed first, but space itself also becomes more complicated once motion approaches the speed of light. One of the most well-known consequences is length contraction. According to special relativity, an object moving very rapidly relative to an observer will appear shortened along the direction of its motion. At first glance, this sounds like a curious optical illusion, perhaps something similar to a visual distortion, but the effect is not about eyesight. It arises from the deeper way measurements of space and time are defined in different frames of motion. To measure the length of a moving object, an observer must determine where both ends of the object are at the same moment in time. That phrase may sound straightforward, yet it contains a hidden assumption. The measurement requires the observer to decide which two events count as happening simultaneously. Because simultaneity depends on the observer's motion, different observers will choose different pairs of events when measuring the same object. The resulting lengths are therefore different. In this sense, length contraction is not something that physically squeezes an object like pressure from outside. Instead, it reflects the geometry of space-time and the procedures used to measure distance. The object itself remains perfectly ordinary within its own frame of motion. This realization had another important consequence. The classical idea of a perfectly rigid body could no longer survive unchanged. In Newtonian mechanics, it was sometimes imagined that objects could move as perfectly rigid structures, here responding instantly to forces across their entire length. Relativity forbids this. No influence can travel faster than the speed of light, including mechanical disturbances within matter. If one end of a long rod is pushed, the disturbance cannot reach the far end instantly. It must propagate through the material at a finite speed. This means rigid bodies in the classical sense cannot exist. Every physical object must obey the same causal structure imposed by space-time. Once motion approaches extremely high speeds, another change becomes visible. Objects begin to resist further acceleration in a dramatic way. In classical physics, momentum is defined as mass multiplied by velocity. Doubling the velocity simply doubles the momentum. The relationship between energy, momentum, and motion is straightforward. Yet relativity alters that relationship. As an object moves faster and faster, its momentum grows more quickly than Newtonian physics would predict. The closer the object approaches the speed of light, the more rapidly this momentum increases. Energy behaves in a similar way. Adding energy to an object increases its speed at first, but as the object approaches the relativistic boundary, more and more energy is required for smaller and smaller gains in velocity. Eventually, the required energy rises so steeply that reaching the speed of light would demand an unlimited amount of energy. Nature never provides such a resource. Early discussions sometimes describe this behaviour by saying that the mass of an object increases with speed. This phrase, often called relativistic mass, appeared in early 20th century explanations of relativity. While historically interesting, modern physics prefers a clearer description. The mass of an object, more precisely its invariant mass, remains constant. What changes with motion are the object's total energy and momentum. These quantities grow dramatically as velocity increases, reflecting how space-time geometry governs motion. Several physicists played important roles in clarifying these ideas during the early decades of relativity. Max von Laue contributed significantly to the interpretation of relativistic dynamics and helped organize the theory into a coherent framework for understanding energy and momentum in moving systems. Wolfgang Pauli later wrote an influential treatise on relativity that carefully explained the conceptual foundations of the theory. Pauli's work helped generations of physicists understand how energy, momentum, and space-time geometry fit together. These conceptual clarifications were soon reinforced by experimental evidence. Particle accelerators provided one of the clearest demonstrations. In these machines, charged particles such as electrons or protons are accelerated using powerful electromagnetic fields. As the particles gain energy, their speeds increase dramatically. Yet even the most energetic particles never exceed the speed of light. Instead, as more energy is added, the particles' momentum continues to grow, while their speed approaches the relativistic boundary ever more slowly. The additional energy goes increasingly into the energy associated with motion, rather than into further increases in velocity. Facilities such as the European Organization for Nuclear Research near Geneva and other major accelerator laboratories around the world have confirmed this behavior with extraordinary precision. Particles in modern accelerators reach speeds so close to the speed of light that the remaining difference becomes extremely small. The energy required to push them closer to that boundary becomes enormous. This behavior follows exactly the predictions of special relativity. It also reveals something important about the nature of matter itself. The inability of objects with mass to reach the speed of light is not simply a technological limitation or an engineering challenge. It is built into the relationship between energy, momentum, and space-time. Matter resists acceleration near the light speed boundary because the geometry of space-time makes further acceleration increasingly costly in terms of energy. From the perspective of the particle itself, nothing unusual happens locally. Its internal physics continues normally. But from the viewpoint of external observers, the energy required to increase its velocity rises steeply. In the language of relativity, the world line of a massive object must remain within the interior of the light cone. The boundary itself belongs only to massless entities such as photons. The practical consequences appear every time scientists attempt to push particles toward higher energies. Even with the most powerful machines ever constructed, matter approaches the speed of light only asymptotically. It gets closer and closer, but it never arrives. This pattern reinforces the central theme that has quietly emerged throughout the development of modern physics. The speed of light is not merely a characteristic of light waves or electromagnetic radiation. It marks a structural boundary embedded within space-time itself. Radiation naturally travels along that boundary. Matter, by contrast, remains confined within it, forever approaching but never crossing the limit. The universe does not prevent matter from outrunning light through some external rule or prohibition. Instead, the structure of energy, motion, and space-time ensures that the boundary cannot be crossed. One of the most famous results of modern physics is the relationship between mass and energy. It is often quoted in a short symbolic form, but its meaning reaches far beyond a single compact expression. The idea behind it is that mass and energy are not separate ingredients of nature. They are different ways of describing the same underlying quantity. Albert Einstein discovered that a body at rest contains energy simply because it possesses mass. Even when an object is perfectly still and not interacting with anything, it carries what physicists call rest energy. That energy is related to the mass of the object and to the same constant that governs the motion of light. Written out in full English, the relationship says that energy equals mass multiplied by the square of the speed of light. This statement may sound like a curious conversion rule, but it reveals something deeper about how nature organizes its bookkeeping. Earlier physics treated mass and energy as distinct concepts. Mass described how much matter an object contained, while energy described the capacity to perform work or produce motion. Relativity unifies these ideas. A small amount of mass corresponds to a very large amount of energy. because the conversion factor involves the square of the same constant that defines the speed of light. Even a tiny quantity of mass therefore represents an enormous reservoir of energy. This principle appears dramatically in nuclear reactions. When atomic nuclei combine or split, a small fraction of their mass is converted into other forms of energy such as heat and radiation. The sun shines because hydrogen nuclei merge into helium inside its core, releasing energy through precisely this process. The mass-energy relationship therefore connects cosmic starlight, nuclear power, and the structure of space-time itself. What makes the constant associated with the speed of light so important is that it appears repeatedly across many different areas of physics. It is not merely the speed at which visible light travels, it acts as a conversion factor linking quantities that older physics treated separately. For example, the constant links measurements of distance and time within spacetime geometry. It also connects energy with momentum in relativistic motion, and appears in the relationship between rest energy and mass. Because of this role, many physicists view the constant less as a property of light and more as a fundamental scale built into the structure of reality. In effect, it converts between the units used to measure time and the units used to measure space. If time is measured in seconds and distance in meters, the constant tells us how those two quantities relate within space-time. This interpretation becomes clearer when examining how modern physics treats conservation laws and symmetries. The mathematician Emmy Noether played a crucial role in clarifying these connections. Her work in the early 20th century showed that whenever the laws of physics possess a symmetry, a corresponding quantity must be conserved. For instance, the symmetry of physical laws under shifts in time leads directly to the conservation of energy. The symmetry under shifts in spatial position leads to the conservation of momentum. These insights reveal that the regularities of nature arise from deep structural principles rather than from arbitrary rules. The constant associated with the speed of light fits naturally within this framework. It expresses a symmetry of space-time itself. Observers moving at constant velocity relative to one another must describe the same laws of physics, and the invariant speed embedded in those laws provides the link that preserves this symmetry. Seen from this perspective, the constant does not belong exclusively to light. It belongs to the architecture of space-time. The interpretation of relativity has been explained in particularly clear ways by thinkers such as Hermann Bondi, and later by Edwin Taylor and John Wheeler in their pedagogical writings. These physicists emphasize that relativity is not mainly about fast rockets or exotic experiments. It is about the structure that keeps measurements of energy, momentum, space, and time consistent for all observers. Once this structure is understood, the constant that first appeared in discussions of light becomes something more universal. Gravitational waves, predicted by Albert Einstein's general theory of relativity, and confirmed a century later by the Laser Interferometer Gravitational Wave Observatory, propagate through space-time at the same invariant speed. These ripples in the fabric of space-time are not made of light at all, yet they follow the same causal boundary. In quantum field theory, particles such as photons are described as excitations of underlying fields. These fields obey equations whose propagation speeds are governed by the same invariant constant. Even hypothetical massless particles in other quantum fields would move according to that same limit. In this way, the constant emerges again and again across the foundations of modern physics. It sets the pace at which signals can travel. It links energy with mass. It determines how observers convert between measurements of space and time, and it establishes the causal structure that prevents influences from propagating arbitrarily fast. For this reason, many physicists prefer to think of the constant not as the speed of light in a narrow sense, but as the fundamental conversion factor that binds space-time together. Light happens to travel at that speed because photons have no rest mass. Their motion naturally follows the boundary built into space-time geometry, but the boundary itself exists independently of visible light. Seen from this angle, the familiar phrase about the speed of light begins to take on a slightly different meaning. The constant does not simply describe how quickly light travels through the universe. It defines how the universe itself measures relationships between space, time, energy, and motion. What first appeared as a property of radiation gradually becomes something more profound. It is a rule that keeps the accounting of reality consistent. Whenever energy transforms into motion, whenever mass converts into energy, whenever signals carry information from one event to another, the same invariant scale quietly appears. Light reveals this constant to us, but the constant belongs to the deeper structure of the universe itself. Light had already forced physicists to rethink space and time, yet at the beginning of the 20th century another surprise appeared. Even the nature of light itself turned out to be stranger than expected. For much of the 19th century, light had been successfully described as a wave. James Clerk Maxwell's theory of electromagnetism showed that oscillating electric and magnetic fields could travel through space as self-propagating waves. This explanation accounted for reflection, refraction, interference, and the spreading colours of the spectrum. But certain experiments refused to behave according to classical wave ideas. One of the earliest clues emerged from the study of heated objects. When a piece of metal is heated, it glows, first red, then orange, then white as the temperature rises. Physicists studying this phenomenon, known as blackbody radiation, discovered that classical physics predicted an impossible result. According to classical theory, hot objects should radiate an unlimited amount of energy at very short wavelengths. This prediction became known as the ultraviolet catastrophe. In 1900, the German physicist Max Planck found a way to match theory with observation. Planck suggested that electromagnetic energy could not be emitted continuously. Instead, it must be released in discrete packets. These packets became known as quanta. At first, Planck treated this idea as a mathematical trick rather than a deep statement about reality. But within a few years, Albert Einstein recognized that the concept might be fundamental. In 1905, Einstein examined a phenomenon called the photoelectric effect. When light shines on certain metals, electrons can be ejected from the surface. Classical wave theory predicted that the energy of the ejected electron should depend on the intensity of the light. Experiments showed something different. The energy of the electrons depended on the frequency of the light rather than its brightness. Even very intense light could fail to eject electrons if its frequency was too low. Einstein explained this behaviour by proposing that light itself arrives in discrete quanta. Each quantum carries a specific amount of energy determined by its frequency. This idea was radical. It suggested that light sometimes behaves not as a smooth wave, but as individual particles. These particles later became known as photons. Over time, additional experiments reinforced this picture. One of the most convincing came from the American physicist Arthur Compton. In the 1920s, Compton studied how high-energy light scattered when it collided with electrons. The scattered light showed a measurable change in wavelength depending on the angle of the collision. This behaviour could be explained if light carried momentum and behaved like a particle during the interaction. The phenomenon became known as the Compton effect. Together, the photoelectric effect and the Compton effect made it clear that light possessed both wave-like and particle-like properties. Neither description alone was sufficient. Quantum theory provided the framework needed to reconcile these behaviours. A crucial step came from the work of Satyendra Nath Bose, an Indian physicist who studied the statistical behaviour of photons. Bose developed a method for counting the possible states of identical particles that do not obey the usual rules of classical distinguishability. Albert Einstein recognised the significance of Bose's work and extended the ideas to other quantum systems. The statistical framework that emerged is now known as Bose-Einstein statistics. Photons belong to this class of particles. Unlike classical objects, photons can occupy the same quantum state without exclusion. This property explains many phenomena in modern physics, including the behaviour of lasers and the collective properties of light in certain conditions. In modern physics, a photon is not simply a tiny billiard ball flying through space. It is better understood as a quantist excitation of the electromagnetic field. According to quantum field theory, fields fill all of space. The electromagnetic field is one such field. When the field vibrates in a particular quantist way, the excitation appears as a photon, where this photon has zero rest mass and always travels at the invariant speed associated with space-time geometry. In other words, the photon does not choose to travel at that speed. Its existence within the structure of the electromagnetic field makes any other speed impossible. As quantum theory developed further, physicists built a remarkably precise description of how light interacts with matter. This theory became known as quantum electrodynamics. Several scientists played major roles in constructing this framework. Richard Feynman developed intuitive diagrams that describe how particles exchange energy through quantum interactions. Julian Schwinger and Shinichiro Tomonaga independently developed mathematically rigorous formulations of the same theory. Freeman Dyson later demonstrated that these approaches were mathematically equivalent, unifying them into a coherent framework. Quantum electrodynamics remains one of the most accurate theories ever created in science. Its predictions have been confirmed experimentally to astonishing precision. Measurements comparing theory and experiment sometimes agree to more than 10 decimal places. Few areas of physics reach that level of accuracy. Within this framework, photons emerge as fundamental carriers of the electromagnetic interaction. They transmit forces between charged particles and propagate through space-time according to the same invariant speed that governs all massless fields. This means that the quantum description of light does not weaken the relativistic speed limit. If anything, it strengthens it. Because photons have zero rest mass, their natural motion follows the boundary defined by space-time itself. They cannot move slower than that limit in a vacuum, and they cannot move faster. Their behaviour reflects the underlying geometry of space-time and the structure of the electromagnetic field simultaneously. The familiar beam of light streaming from a lamp or arriving from a distant star therefore represents something surprisingly deep. Each photon is a ripple in the electromagnetic field, carrying energy and momentum while respecting the invariant structure of space-time. Wave and particle descriptions both capture part of this behaviour. Neither picture alone is complete, yet together they reveal a phenomenon that has become one of the most thoroughly understood in all of physics. Light once appeared mysterious and intangible. Modern quantum theory has revealed it as a remarkably precise and well-described feature of nature, and yet, even in this refined picture, the same fundamental boundary remains in place. Photons travel exactly along the limit built into space-time itself. The speed of light is therefore not merely a property of electromagnetic radiation. It is woven into the deepest description of how the electromagnetic field exists within the universe. The picture of light as a photon already begins to stretch everyday intuition, yet modern physics takes the idea even further. In the framework known as quantum field theory, the basic ingredients of reality are not tiny particles moving through empty space. Instead, the universe is filled with fields that extend everywhere. Particles are best understood as excitations of those fields. In this picture, the electromagnetic field exists throughout all of space. A photon appears when that field vibrates in a particular quantized way. The photon is not a little object travelling through an otherwise empty void. It is a ripple in something that is already present everywhere. Once this idea is taken seriously, the concept of empty space begins to change dramatically. Classical physics imagined the vacuum as a perfect emptiness, a stage on which objects and forces acted, but which had no structure of its own. Modern quantum theory replaces that quiet emptiness with something far richer. The vacuum becomes the lowest energy state of all the fields filling the universe. Even in this lowest energy state, the fields cannot remain perfectly still. Quantum theory allows fluctuations that briefly create and destroy tiny disturbances within the fields. These fluctuations do not produce long-lived particles under ordinary conditions, yet their presence can still influence measurable phenomena. The idea that the vacuum contains activity rather than absolute nothingness emerged gradually during the development of quantum field theory. One of the early contributors to this framework was Pascual Jordan, who helped apply quantum ideas to electromagnetic fields and played a key role in the birth of field quantization. Another figure sometimes overlooked in popular accounts is Ettore Majorana, whose work explored the mathematical structure of relativistic fields and particles. Majorana investigated ways in which particles might be described through symmetries and field properties rather than through classical mechanical pictures. These developments pushed physics toward a view in which fields, rather than particles, became the primary ingredients of reality. The consequences of this shift began to appear in subtle, experimental effects. One example is vacuum polarization. According to quantum field theory, the electromagnetic field interacting with charged particles can momentarily create virtual pairs of particles and antiparticles. These pairs exist only briefly before annihilating again, yet their temporary presence alters how electric charges interact across space. Another striking phenomenon is the Casimir effect. When two extremely smooth metal plates are placed very close together in a vacuum, a tiny attractive force appears between them. This force arises because the quantum fluctuations of fields behave slightly differently between the plates than they do in the surrounding space. The result is a measurable pressure produced by the structure of the vacuum itself. These effects do not mean that particles are constantly popping into existence in the everyday sense. Rather, they reveal that the vacuum contains a rich mathematical structure shaped by the behaviour of underlying fields. In modern particle physics, these ideas are organised within a framework known as the Standard Model. This theory describes several fundamental fields and the particles associated with them. The electromagnetic field gives rise to photons. Other fields describe particles such as electrons, quarks, and neutrinos. Additional fields correspond to the carriers of fundamental forces, including the particles that mediate the weak nuclear interaction and the strong nuclear interaction. Many of these force-carrying particles belong to a class known as gauge bosons. The photon is one example of a gauge boson associated with the electromagnetic interaction. These particles arise from symmetries known as gauge symmetries that govern how fields transform under certain mathematical operations. Although the details of these symmetries can become highly technical, the overall picture remains surprisingly elegant. The behaviour of particles and forces emerges from the symmetries and interactions of underlying fields. Within this framework, the propagation of disturbances through a field must obey strict rules. One of the most important is the principle of locality. Locality means that physical interactions occur through neighbouring points in space-time, rather than through instantaneous action at a distance. A disturbance in a field can influence nearby regions first and then spread outward over time. Because of this requirement, the propagation of signals in relativistic field theory is constrained by causality. Influences cannot leap instantly from one place to another. Instead, disturbances travel outward at speeds limited by the structure of space-time. For fields associated with massless particles such as photons, the natural propagation speed is exactly the invariant speed that appears throughout relativity. This means that the speed of light is not merely an experimental observation about electromagnetic radiation. It arises naturally from the combination of space-time geometry and the principles governing field interactions. A ripple in the electromagnetic field spreads through space according to those rules. The boundary defined by space-time determines how quickly that ripple can move. Other fields obey similar restrictions. Even when the particles associated with a field possess mass and therefore move more slowly than light, the fundamental equations describing the field still respect the same causal boundary. In this way, the speed limit associated with light becomes embedded in the very logic of relativistic field theory. Signals propagate through fields in a way that preserves causality and prevents influences from travelling faster than the structure of space-time allows. The vacuum itself therefore participates in this story. Because the vacuum is the ground state of all the fields filling the universe, it carries the same geometric and causal structure. The fields may fluctuate, interact, and produce particles under the right conditions, but they always respect the same underlying limits. Empty space turns out not to be simple at all. It is a dynamic stage filled with fields, symmetries, and subtle fluctuations. Those fields define how particles exist, how forces propagate, and how signals move across the universe. And within this intricate structure, the familiar constant associated with the speed of light quietly appears once again, not merely as a feature of photons, but as the natural pace at which disturbances can move through the fabric of the fields themselves. When people first hear that nothing can travel faster than light, the statement often sounds like a rule about motion. It is easy to imagine it as a speed limit similar to those placed on roads, a restriction on how quickly objects are allowed to move through space. Yet in modern physics, the deeper meaning of the limit lies elsewhere. The boundary associated with the speed of light is fundamentally a limit on the transmission of signals and the transfer of information. It governs how influences spread through the universe and how events can affect one another. To understand why this matters, it helps to think about what it means for one event to cause another. If a star explodes in a distant galaxy, the explosion can influence other regions only after information about the event has travelled outward. That information may be carried by light, by gravitational waves, or by other forms of radiation. But the message must travel. It cannot appear instantly everywhere. And relativity tells us that signals carrying information cannot propagate faster than the invariant speed built into spacetime. This constraint preserves the logical order of cause and effect. An event must occur before its influence can be observed elsewhere. The geometry of space-time ensures this ordering by organizing events into the familiar structure of light cones. If an event lies outside another event's light cone, then no signal travelling at or below the allowed speed can connect them. This region of space-time remains causally disconnected. If signals could travel faster than the speed of light, this structure would collapse. Messages could be sent into regions that lie outside the light cone. Under certain circumstances, those messages could even arrive before they were sent according to some observers. The result would be deeply paradoxical. Imagine sending a message to prevent an event that already caused the message to be sent in the first place. Such loops of cause and effect would make it impossible to define a consistent narrative order for events. Relativity avoids these paradoxes by enforcing a universal boundary on how quickly information can travel. Within this framework, locality becomes a central principle. Locality means that interactions occur through neighbouring regions of space-time rather than through instantaneous connections across arbitrary distances. Fields interact with nearby points first, and disturbances spread outward gradually. This behaviour preserves the causal structure defined by the light cones of space-time. The relationship between causality and information becomes even more interesting when quantum mechanics enters the story. Quantum systems can exhibit correlations that seem surprisingly strong across large distances. These correlations are most famously associated with a phenomenon known as quantum entanglement. When two particles become entangled, measurements performed on one particle can be correlated with measurements performed on the other, even if the particles are separated by enormous distances. This behaviour puzzled physicists for many years. The physicist John Bell eventually developed a mathematical framework known as Bell's theorem, which demonstrated that quantum correlations cannot be explained by certain kinds of hidden classical variables. Experiments performed over the past several decades have repeatedly confirmed that these correlations are real features of quantum systems. At first glance, this might seem to suggest that information is somehow travelling faster than light between the entangled particles. However, the situation is more subtle. Although entangled particles share correlations, those correlations cannot be used to transmit controllable messages faster than light. The outcomes of individual measurements remain fundamentally unpredictable. observers cannot manipulate the results in a way that sends meaningful information instantly across space. This constraint is known as the no-signaling principle. It ensures that even within the strange framework of quantum mechanics, the causal structure of relativity remains intact. Entanglement can produce correlations that appear instantaneous, but it cannot be used to send signals that outrun light. Several thinkers explored the deeper implications of these ideas. David Bohm developed an interpretation of quantum mechanics that emphasized the role of non-local connections within the quantum wave function. Although Bohm's interpretation allowed for hidden variables guiding particle behaviour, it still preserved the observable limits on signal transmission. Abner Shimony later examined the philosophical consequences of quantum correlations, describing the phenomenon as a kind of peaceful coexistence between quantum non-locality and relativistic causality. Quantum theory allows surprising patterns of correlation, yet it does not permit communication that would violate the causal order established by relativity. These discussions highlight an important point. The speed associated with light is not simply about how fast particles move, it determines how information can flow through the universe. Every signal, every message, every causal influence must obey the same boundary. Whether the signal is carried by light, by electromagnetic waves, by gravitational disturbances, or by any other physical process, the structure of space-time imposes the same limit. Without that limit, the logical consistency of the universe would break down. Events could influence the past. Messages could arrive before they were sent. Observers could construct paradoxical loops of cause and effect that undermine any coherent timeline. The light-speed boundary prevents these possibilities. It preserves a stable ordering of events in which causes led to effects and signals propagate outward through space-time. In this sense, the limit associated with light is one of the quiet guardians of physical reality. It ensures that the universe has a consistent narrative structure. Stars explode before their light reaches distant observers. Signals leave transmitters before they arrive at receivers. Causes precede their consequences in every observer's description of events. The geometry of space-time, the behaviour of fields, and the logic of information all converge on the same rule. Influence spreads outward through the universe no faster than the boundary defined by light itself. That rule allows the cosmos to maintain a coherent story unfolding across space and time. And looking into the night sky can feel like looking outward into vast distances. Yet in cosmology, every glance toward a distant object is also a glance backward in time. The reason is simple, but profound. Light does not arrive instantly, it travels. When a telescope observes a galaxy millions of light years away, the light entering the instrument began its journey millions of years ago. The galaxy appears not as it is now, but as it was when that light first departed. Astronomy is therefore a form of time travel through observation. The deeper scientists look into space, the further back in cosmic history they're seeing. Nearby stars reveal recent events on the scale of years or centuries. Distant galaxies show scenes that unfolded long before human civilization existed. The most remote objects observable today display conditions from billions of years in the past. This remarkable situation arises directly from the finite speed at which light moves through space-time. The expansion of the universe adds another layer to the story. In the early 20th century, astronomers began noticing that light from distant galaxies appeared slightly stretched toward the red end of the spectrum. This phenomenon became known as redshift. The American astronomer Vesto Slipher was among the first to measure these shifts carefully. Later, Edwin Hubble compared galaxy distances with their redshifts and found a striking pattern. Galaxies appeared to be moving away from one another, and the more distant a galaxy was, the faster it seemed to recede. This discovery suggested that space itself is expanding. The Belgian physicist and priest Georges Lemaitre had already proposed a similar idea from theoretical considerations. Lemaitre argued that the equations of general relativity allowed the universe to grow over time rather than remain static. Together, these observations and theoretical insights transformed cosmology. The universe was no longer imagined as eternal and unchanging. Instead, it possessed a dynamic history. Because light travels at a finite speed, this expanding universe contains natural boundaries known as horizons. One important boundary is the particle horizon. This horizon marks the maximum distance from which light has had time to reach us since the beginning of cosmic expansion. Objects beyond this boundary may exist, but their light has not yet had enough time to arrive. Another concept is the cosmological event horizon. This boundary arises because space itself continues to expand. In some regions of the universe, galaxies move away from us so rapidly, due to cosmic expansion, that their light will never reach Earth, no matter how long the universe continues to evolve. These horizons are not physical walls floating in space. They are limits defined by the relationship between cosmic time, the expansion of the universe, and the speed at which signals can travel. Together they determine which parts of the cosmos are observable and which remain forever beyond reach. The most ancient light currently visible in the universe comes from a faint glow known as the cosmic microwave background. This radiation was first detected in the 1960s and represents light released when the universe was only a few 100,000 years old. At that time, the universe cooled enough for electrons and protons to combine into neutral atoms. Once this happened, radiation could travel freely through space without constant scattering. The cosmic microwave background therefore carries information from an extremely early stage of cosmic history. Space missions have studied this radiation with extraordinary precision. Observatories operated by organisations such as the National Aeronautics and Space Administration and the European Space Agency have mapped tiny variations in the temperature of this ancient light. One particularly detailed survey was conducted by the Planck mission, which produced a precise map of the cosmic microwave background across the entire sky. These measurements revealed subtle patterns that encode information about the early universe and the growth of cosmic structure. Cosmologists such as Jim Peebles have helped develop the theoretical framework that explains how galaxies and clusters of galaxies formed from tiny density variations in the early universe. Peebles' work linked the statistical properties of the cosmic microwave background with the later evolution of cosmic structure. Other thinkers explored related questions about the origin and dynamics of the universe. Dennis Sciama investigated ideas about the connection between inertia and cosmic matter, while Yakov Zeldovich made important contributions to the understanding of large-scale structure formation and the role of gravitational collapse in shaping galaxies and clusters. All of these investigations rely fundamentally on the finite speed of light. Without that limit, the universe would appear entirely different. Observers would see every region of space as it exists now rather than as it was in the past. The concept of cosmic history would become far more difficult to reconstruct. Because light takes time to travel, the universe presents itself as a layered archive of its own past. Nearby objects reveal recent chapters of cosmic evolution, while distant objects reveal earlier ones. In this sense, the speed of light shapes not only the physics of motion, but also the structure of knowledge. There is a practical boundary to what humanity can observe. Even the most powerful telescopes can study only the portion of the universe whose light has had time to reach Earth since cosmic expansion began. Beyond that boundary lies a vast region that may exist but remains inaccessible to observation. Cosmology therefore carries a quiet reminder of the role played by the light speed limit. It does not merely restrict how quickly spacecraft might travel or how rapidly signals can be sent. It defines the horizon of human knowledge. Every star, galaxy, and ancient radiation signal that reaches our instruments has travelled along the causal pathways allowed by spacetime. These signals form the evidence from which scientists reconstruct the history and structure of the universe. Beyond the horizon lies a region that remains silent to us, not because it lacks events or galaxies, but because the signals from those places have not yet arrived. The universe reveals itself gradually through light that has been travelling across cosmic distances for immense spans of time. What we see tonight is therefore a tapestry woven from countless journeys made by photons over billions of years. Each beam of light carries a fragment of cosmic history, arriving precisely at the pace allowed by the deep structure of space-time. Once the idea that nothing can travel faster than light became widely known, it quickly attracted curiosity and occasional confusion. After all, science thrives on exceptions. Whenever a rule appears universal, people naturally begin searching for cases where it might fail. Over the years, several phenomena have been described using language that sounds as though something has outrun light. These examples often circulate widely in popular discussions, sometimes presented as loopholes in relativity, yet when examined carefully, none of them actually violate the light-speed boundary that governs signals and causal influence. One common source of misunderstanding comes from the behaviour of waves. When waves travel through certain materials or mathematical systems, the peaks of those waves can appear to move faster than light. This situation is often described using the concept of phase velocity. Phase velocity refers to how quickly a repeating pattern of peaks and troughs moves through space. In some circumstances, this pattern can shift faster than the speed of light without transmitting any actual signal. To understand why this is possible, imagine shining a laser pointer across the surface of the moon and sweeping it quickly from one side to the other. The dot of light on the moon's surface might appear to move across the lunar landscape extremely rapidly. In principle, it could sweep from one crater to another faster than light could travel between those points. Yet nothing physical travels along the lunar surface in that motion. The dot is simply the changing intersection of a beam arriving from Earth. No information or energy moves faster than light across the moon itself. Wave patterns can behave in a similar way. Another concept that sometimes appears to exceed the speed of light is group velocity. In wave physics, group velocity describes how the overall envelope of a wave packet moves through space. Under certain unusual conditions in specially prepared materials, experiments have produced wave patterns whose group velocities appear faster than light. At first glance, this sounds alarming, but careful analysis shows that the front edge of the signal, the part that carries genuinely new information, still propagates no faster than the light speed boundary. This distinction was studied carefully by physicists such as Arnold Sommerfeld and Léon Brillouin in the early 20th century. Their work clarified how signals propagate through dispersive media and demonstrated that the true signal velocity always respects relativistic causality. The apparent superluminal motion of wave patterns arises from the reshaping of the wave packet rather than from any physical entity outrunning light. Another phenomenon sometimes mentioned in discussions of faster-than-light motion is Cherenkov radiation. This effect occurs when a charged particle travels through a transparent medium, such as water. Faster than light can move through that same medium. At first, this sounds like a direct violation of relativity. But the key detail lies in the phrase "through that medium." Light travels more slowly in materials such as water or glass than it does in a vacuum. The particle generating Cherenkov radiation is not exceeding the universal speed limit set by space-time. It is simply moving faster than light, propagates within that particular substance. The result produces a faint blue glow, often visible in nuclear reactors, caused by a shock wave of electromagnetic radiation similar in spirit to the sonic boom produced by aircraft exceeding the speed of sound in air. In both cases, the fundamental limit associated with the speed of light in empty space remains intact. Cosmology introduces another situation that can appear puzzling. Because the universe is expanding, distant galaxies can recede from us at speeds greater than the speed of light when measured across very large distances. This observation does not violate relativity either. The galaxies themselves are not racing through space faster than light. Instead, the space between galaxies is stretching as the universe expands. The recession speed reflects the growth of space-time geometry rather than motion through space-time. This distinction between movement within space-time and changes in space-time itself is essential for understanding modern cosmology. The difference becomes clearer when imagining dots drawn on the surface of an inflating balloon. As the balloon expands, the dots move farther apart, even though they are not travelling across the rubber surface themselves. Similarly, galaxies remain relatively stationary within their local regions of space, while cosmic expansion increases the distance between them. Theoretical physics has also explored the possibility of particles that might always travel faster than light. These hypothetical entities are known as tachyons. The idea appeared in the 1960s as physicists investigated the mathematical consequences of relativistic equations. If particles existed with imaginary rest mass in certain equations, they would necessarily move faster than the light speed boundary. Such particles would behave in unusual ways. They could never slow down to reach the speed of light from above. Instead, they would always remain in the superluminal regime. Although intriguing from a theoretical standpoint, no experimental evidence has ever confirmed the existence of tachyons. Most physicists treat the concept as a mathematical curiosity rather than a realistic prediction. Nevertheless, the study of such possibilities plays an important role in theoretical physics. By examining the consequences of hypothetical scenarios, scientists can better understand why certain principles such as relativistic causality appear necessary for a consistent description of the universe. Taken together, nearly these examples illustrate how easily misunderstandings can arise when discussing the speed of light. Many phenomena involve velocities or patterns that appear to exceed that limit in superficial ways. But when the definitions are examined carefully, the central rule remains intact. No object carrying mass, no signal conveying information, and no causal influence propagates faster than the invariant boundary defined by spacetime. The distinction between appearances and genuine violations becomes particularly important in an age where fragments of scientific ideas often circulate widely without their original context. Careful physics reminds us that the speed limit associated with light is not a fragile rule waiting to be broken. It is woven deeply into the structure of relativity, quantum field theory, and the logic of causality itself. Right understanding where apparent exceptions come from helps clear the ground for deeper questions. Once misconceptions are set aside, the real mysteries surrounding the structure of spacetime can be explored with clarity, and those mysteries turn out to be even more fascinating than the myths that sometimes surround them. The light speed boundary appears so deeply embedded in physics that it is natural to wonder whether there might be ways around it. Not by breaking the rules locally, but by exploiting the geometry of space-time itself. General relativity, the theory developed by Albert Einstein to describe gravity, does not treat space and time as rigid backgrounds. Instead, space-time behaves like a flexible structure that can bend, stretch, and curve in response to matter and energy. This flexibility opens the door to some surprising possibilities. One idea that has captured both scientific and popular imagination is the concept of a wormhole. A wormhole is a hypothetical tunnel connecting two distant regions of space-time. Instead of travelling across the enormous distance separating those regions, a traveller could move through the tunnel and emerge somewhere far away. In principle, such a shortcut would allow a journey that appears faster than light when viewed from the outside. The concept of wormholes became widely studied after the work of physicists Michael Morris and Kip Thorne in the 1980s. They explored whether Einstein's equations permit stable passages through space-time that could remain open long enough for signals or travellers to pass through. Their analysis showed that general relativity does allow solutions with this kind of geometry. However, these solutions come with a serious challenge. To keep a wormhole open, the equations require a form of matter with unusual properties. This matter would need to possess negative energy density relative to ordinary vacuum conditions. In simple terms, the energy associated with the material would have to behave in ways that ordinary matter never does. Theoretical physicist Matt Visser later explored these geometries in greater depth, analysing the mathematical structure of wormholes and the conditions required for them to remain stable. Visser's work emphasised that while general relativity allows such solutions mathematically, the physical ingredients required to realize them remain uncertain. A related idea involves the concept of a warp drive. Instead of travelling through space-time faster than light, a warp drive would attempt to move space-time itself. The most famous version of this idea was proposed by Miguel Alcubierre in the 1990s. In the Alcubierre model, space-time would be compressed in front of a spacecraft and expanded behind it. The craft would sit inside a bubble of space-time that effectively carries it forward. Inside the bubble, the spacecraft would remain locally stationary. The surrounding geometry would do the moving. From the perspective of distant observers, the bubble could move faster than light relative to distant regions of space, even though nothing inside the bubble exceeds the local speed limit. Like wormholes, however, the warp drive solution requires exotic forms of energy. The space-time geometry needed to create the warp bubble depends on regions of negative energy density. This requirement brings the discussion back into contact with quantum field theory. Under ordinary circumstances, energy densities are positive. Matter, radiation, and most known physical systems contribute positive energy to space-time. Negative energy appears only in very subtle contexts. One example arises in the Casimir effect, where two closely spaced metal plates alter the vacuum fluctuations of quantum fields between them. The resulting configuration can produce a small region where the energy density becomes slightly lower than the surrounding vacuum. This effect has been measured experimentally, confirming that quantum fields can indeed produce energy configurations that deviate from classical expectations. However, the magnitude of these effects is extremely small. The negative energy densities produced in laboratory conditions are tiny and exist only across microscopic distances. To sustain a wormhole or warp bubble large enough for practical travel would require quantities of exotic energy far beyond anything currently known. Physicists studying these possibilities must therefore consider additional constraints. Quantum field theory imposes restrictions known as quantum inequalities, which limit how much negative energy can exist in a region and for how long. These inequalities were developed through work by several researchers examining how quantum fluctuations behave in curved space-time. The results suggest that negative energy cannot be accumulated or maintained indefinitely. In other words, nature may permit small and temporary departures from classical energy conditions, but not the enormous concentrations required for large-scale space-time engineering. The result is a delicate balance between mathematical possibility and physical plausibility. General relativity allows a wide range of geometric solutions. Some of these solutions include wormholes, warp metrics, and other unusual space-time structures. The equations themselves do not forbid them outright. Yet when quantum field theory and energy conditions are taken into account, the requirements become far more restrictive. This situation illustrates an important aspect of theoretical physics. Exploring speculative solutions helps scientists understand the boundaries of known theories. By examining extreme possibilities, my researchers can test how robust the principles of relativity and quantum mechanics truly are. Most of these ideas remain firmly within the realm of speculation. There is currently no experimental evidence that wormholes exist in nature, nor any indication that warp drive geometries can be constructed using realistic physical resources. These concepts remain mathematical explorations rather than technological prospects. Yet they serve a useful purpose. They highlight how deeply the light-speed boundary is woven into the structure of physics. Even attempts to circumvent the limit must do so indirectly, by reshaping space-time itself, rather than by sending objects racing through space faster than light. The boundary remains intact locally. Signals within any small region of space-time still obey the same causal structure. The familiar limit continues to govern how information and influence propagate. The imaginative landscape of theoretical physics therefore stretches far beyond everyday experience. Yet it remains guided by careful reasoning and empirical restraint. Some possibilities remain open questions. Others appear unlikely given current knowledge. For now, the light speed limit stands as one of the most reliable principles in modern physics, shaping both the everyday behaviour of matter and the farthest reaches of speculative thought. Even the most adventurous ideas must still find their place within the quiet geometry that space-time allows. Gravity is often imagined as something silent and immediate, a force quietly pulling objects toward one another across the vast distances of space. For much of scientific history, that picture seemed reasonable. Isaac Newton's theory of gravity described gravitational attraction as an instantaneous influence acting across empty space. Yet the development of relativity changed that picture profoundly. In the framework of general relativity, gravity is not a force transmitted through space in the traditional sense. Instead, gravity reflects the curvature of space-time itself. Massive objects such as stars and planets distort the geometry around them, shaping the paths that nearby objects follow. Crucially, these distortions cannot change instantly. When a massive body moves or undergoes a violent event, the resulting changes in space-time geometry propagate outward as waves. These disturbances travel at the same invariant speed that governs light and all other massless phenomena. The existence of these disturbances, known as gravitational waves, was predicted by Albert Einstein in the early 20th century. For decades, the idea remained largely theoretical. The waves predicted by general relativity are extraordinarily faint by the time they reach Earth. Detecting them requires instruments capable of measuring changes in distance far smaller than the diameter of an atomic nucleus. One of the earliest researchers to attempt such a detection was Joseph Weber in the 1960s. Weber constructed large aluminium cylinders designed to vibrate when a passing gravitational wave stretched and compressed space. Although his experiments sparked enormous interest, later investigations failed to confirm the signals he believed he had observed. The search for gravitational waves continued, gradually becoming more sophisticated. Eventually, the effort culminated in one of the most remarkable experimental achievements in modern physics. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, was designed to detect minute distortions of space-time using laser interferometry. Two facilities in the United States, separated by thousands of kilometers, measure the relative lengths of long vacuum tunnels as laser beams bounce back and forth between precisely positioned mirrors. When a gravitational wave passes through Earth, it stretches space in one direction while compressing it in another. The change is incredibly small, yet sensitive instrumentation can detect the resulting shift in the interference pattern of the laser beams. This ambitious project grew from decades of theoretical and experimental groundwork. Rainer Weiss played a crucial role in developing the interferometer design, while Kip Thorne and Ronald Drever helped establish the broader theoretical and experimental program that eventually led to the observatory's construction. In 2015, the collaboration achieved the first direct detection of gravitational waves. The signal originated from the merger of two black holes more than 1 billion light-years away. As the black holes spiraled together, they radiated gravitational waves that rippled across the universe. By the time those waves reached Earth, they altered the length of the interferometer arms by a distance smaller than a proton. The measurement confirmed a prediction that had stood for a century. It also demonstrated that gravity communicates changes at the same fundamental speed that governs light. An even more striking confirmation came a few years later when astronomers observed the merger of two neutron stars. This event produced both gravitational waves and electromagnetic radiation. Gravitational wave detectors recorded the ripples in space-time first. Moments later, telescopes around the world detected flashes of light from the same cosmic event. The difference in arrival times between the gravitational waves and the electromagnetic signals was extraordinarily small considering the immense distance the signals had travelled. Both forms of information had crossed hundreds of millions of light-years of space at essentially the same speed. This observation provided powerful evidence that gravitational disturbances and electromagnetic radiation share the same causal speed scale. The result reinforces a remarkable unity in physics. The light, gravitational waves, and other massless excitations all propagate according to the same invariant boundary built into space-time. Yet this unity also raises deeper questions. Modern physics rests upon two extraordinarily successful theories. General relativity describes the behaviour of space-time and gravity across cosmic distances. Quantum field theory describes the behaviour of particles and fields at microscopic scales. Both frameworks treat the invariant speed associated with light as a foundational constant. In relativity, it defines the structure of space-time itself. In quantum field theory, it determines how fields propagate and how causality is preserved in particle interactions. Despite their successes, the two frameworks remain difficult to reconcile. Physicists seeking a deeper understanding of gravity and quantum theory have explored many different approaches. Bryce DeWitt helped pioneer the study of quantum gravity, attempting to apply quantum principles to the geometry of spacetime itself. Roger Penrose has proposed ideas linking spacetime structure, black hole physics, and quantum processes in unexpected ways, exploring whether gravity might play a role in fundamental aspects of quantum measurement. Abhay Ashtekar developed a reformulation of general relativity that led to loop quantum gravity, an approach in which spacetime geometry becomes quantized at extremely small scales. Ted Jacobson has explored the possibility that Einstein's equations might emerge from deeper thermodynamic principles, suggesting that spacetime itself could arise from underlying statistical behaviour. Each of these approaches represents a different attempt to understand what lies beneath the familiar structure of spacetime. The invariant speed associated with light sits at the centre of this puzzle. It appears repeatedly in equations describing relativity, quantum fields, and causal structure. It governs the behaviour of photons, gravitational waves, and all massless particles. Yet physicists still debate why this particular speed plays such a universal role. One possibility is that the invariant speed is simply a fundamental feature of nature, an irreducible constant built into the structure of reality. Another possibility is that it reflects a deeper symmetry of space-time, known as Lorentz symmetry, which constrains how physical laws remain consistent for different observers moving relative to one another. A more speculative view suggests that space-time itself might emerge from a deeper layer of physics. If that is true, the invariant speed might arise as a large-scale property of that deeper structure, rather than as a primitive ingredient. These questions remain open. For now, experiments continue to confirm that the same boundary governs light, gravity, and every known form of information transfer in the universe. The discovery of gravitational waves did more than open a new window on cosmic events. It revealed that the fabric of space-time itself obeys the same quiet rule that governs beams of light crossing the darkness. Across the vastness of the cosmos, whether through radiation or through ripples in geometry, the universe carries its messages at a shared and unyielding pace. After travelling through electromagnetism, relativity, quantum physics, and cosmology, the same quiet boundary continues to appear. Light moves at a particular speed, and nothing carrying information outruns it. The rule emerges again and again, not as an isolated detail, but as a structural feature woven deeply into the laws of nature. Yet this repetition naturally leads to a deeper question. Why does this limit exist at all? At first glance, the answer might appear straightforward. In the framework of relativity, the invariant speed arises from the geometry of spacetime itself. The structure of spacetime defines the relationship between distance and duration in such a way that all observers agree on one particular speed. That agreement is encoded in a symmetry known as Lorentz invariance. This symmetry ensures that the laws of physics look the same for observers moving at constant velocity relative to one another. It reshapes the concept of time and space so that measurements of length and duration adjust in precisely the way needed to preserve the same fundamental speed for all observers. From this perspective, the speed associated with light is not simply the speed of a particular phenomenon. It is the conversion factor that links space and time within the geometry of spacetime. In other words, the limit appears because the structure of spacetime demands it. But this explanation raises another question. Why does spacetime possess this particular structure? Electromagnetism offers a partial clue. When James Clerk Maxwell developed the equations describing electric and magnetic fields in the 19th century, those equations naturally predicted waves travelling at a specific speed. That speed matched the measured speed of light, revealing that light itself is an electromagnetic wave. Later developments showed that Maxwell's equations are automatically consistent with Lorentz symmetry. The mathematics of electromagnetism fits perfectly into the relativistic structure of spacetime. In quantum field theory, the picture becomes even richer. Fields fill space, and particles emerge as excitations of those fields. The propagation of disturbances within these fields follows the causal structure imposed by relativity. In this framework, the invariant speed governs how quickly changes in one region of a field can influence another region. The same boundary shapes the behaviour of photons, gluons, and other massless particles. The limit therefore appears not just in optics or relativity, but in the deeper architecture of quantum fields. Yet even this elegant synthesis may not be the final layer of explanation. Some physicists suspect that spacetime itself could be an emergent structure, arising from deeper microscopic principles. If that idea proves correct, then the invariant speed might also emerge from more fundamental physics, operating at scales far smaller than atoms. Several modern research programs explore this possibility. One approach, known as causal set theory, developed by researchers such as Raphael Sorkin, suggests that spacetime might consist of discrete elements connected by causal relationships. In this picture, the geometry of spacetime emerges from an underlying network that preserves the ordering of cause and effect. If the universe truly has such a discrete causal structure, the familiar spacetime continuum might be a large-scale approximation of a deeper layer of reality. Another approach, known as loop quantum gravity, has been developed by physicists including Carlo Rovelli and Abhay Ashtekar. This theory attempts to quantize spacetime itself, proposing that geometry is built from tiny units, connected in a network often described as spin networks. In this framework, the smooth fabric of spacetime could arise from an underlying quantum structure. The invariant speed might then reflect the behaviour of these microscopic building blocks when viewed at large scales. Fotini Markopoulou has explored related ideas suggesting that spacetime geometry might emerge from more fundamental quantum systems in which space and time are not initially defined at all. From that perspective, the geometry of spacetime would appear only when large numbers of microscopic degrees of freedom interact in a particular way. Another line of investigation involves the concept of asymptotic safety in quantum gravity. Researchers such as Stephen Carlip and others have examined whether gravity might become well behaved at extremely high energies through a special type of mathematical behaviour known as a fixed point. If gravity remains consistent at these extreme scales, it might help unify relativity and quantum theory without introducing entirely new ingredients. Across these different approaches, an intriguing possibility appears repeatedly. The symmetry associated with Lorentz invariance might itself emerge from deeper physics, rather than being fundamental from the beginning. In such scenarios, the invariant speed would arise naturally at large scales, even if the underlying microscopic theory does not initially contain spacetime as it is currently understood. Experiments continue to test this idea. Physicists have searched carefully for tiny deviations from Lorentz symmetry that might hint at deeper layers of structure. Observations of high-energy particles from distant astrophysical sources, precise measurements in particle accelerators, and studies of atomic systems have all been used to probe whether the symmetry holds perfectly. So far, the results place extremely tight limits on any possible violation. Within current experimental precision, Lorentz symmetry appears exact. This remarkable consistency suggests that the invariant speed associated with light is not a fragile feature of one particular theory. Instead, it seems to reflect a deeper regularity in the structure of the universe. Even so, the ultimate explanation remains uncertain. Physics can describe how the limit arises within established frameworks. It can show how space-time geometry, electromagnetic theory, and quantum fields all incorporate the same boundary. But whether that boundary is a fundamental property of reality, a symmetry principle emerging from deeper dynamics, or a large-scale consequence of microscopic physics, remains an open question. This uncertainty is not a weakness of science. It is a sign that the frontier remains active. What is known with great confidence is that the invariant speed associated with light governs the relationships between motion, time, and causality throughout the observable universe. Light does not merely travel quickly. Its behaviour reveals the deeper structure of space-time itself. In following the path of light, physics has uncovered the framework within which events unfold, signals propagate, and the story of the cosmos is written. And that quiet boundary continues to guide every chapter of that story. Across the long history of scientific thought, the speed associated with light has slowly transformed from a curious observation into one of the deepest organizing principles in physics. Early thinkers such as Ibn al-Haytham explored the nature of light through careful experiments with reflection and vision. Centuries later, Endiole Ruma revealed that light does not travel instantaneously by studying the motion of Jupiter's moons, while Christian Huygens proposed that light behaves as a wave moving through space. The 19th century brought a profound leap forward when James Clerk Maxwell unified electricity and magnetism into a single theory of electromagnetic fields. His equations predicted waves travelling at a specific speed, revealing that light itself was an electromagnetic phenomenon. From that point onward, the speed of light was no longer merely an astronomical curiosity. It had become a feature written directly into the laws of nature. The 20th century deepened this insight dramatically. Henri Poincaré and Hermann Minkowski clarified the geometric structure underlying relativity. It is showing that space and time form a unified space-time whose structure preserves a single invariant speed. Quantum theory added another layer of understanding, with figures such as Satyendra Nath Bose helping to define the statistical behaviour of photons, while Emmy Noether revealed the deep connection between symmetries and conservation laws. As physics expanded outward toward the larger scales of the cosmos and inward toward the smallest constituents of matter, the same limit continued to appear. It governs how gravitational waves ripple across space-time, how signals travel through quantum fields, and how distant galaxies are observed through the expanding universe. Even the most imaginative modern ideas must still respect this boundary. Theoretical proposals involving wormholes or warp geometries, explored by researchers such as Miguel Alcubierre, remain bound by the same underlying structure of space-time. Meanwhile, physicists like Carlo Rovelli continue to explore whether space-time itself might emerge from deeper quantum principles. Through all of these developments, one idea remains strikingly consistent. The speed associated with light is not simply the speed at which illumination crosses a dark room. It marks the boundary of causation, the limit governing how events influence one another, and the organizing principle behind the geometry of the universe. It shapes how humans measure time and distance, how black holes trap information, how cosmic horizons limit what can ever be observed, and how particles interact in the microscopic world. Physics has revealed what this limit does with extraordinary clarity. The universe obeys it with remarkable precision across every scale that has been tested. Yet the deeper question still lingers quietly at the edge of knowledge. Science understands how this boundary arises within the theories that describe reality today, but the ultimate reason why the universe possesses such a limit may still lie beyond the frontier of present understanding. For now, the light that crosses the cosmos continues to carry more than illumination. It carries the structure of space-time itself, quietly revealing the rules that allow the universe to remain coherent, connected, and comprehensible.